Hello everyone. Today we're going to be talking about another slightly out there subject, specifically the Rust typing system. It's a bit of a rabbit hole which I fell down into as a result of some very weird circumstances. So I guess to begin in this story, we have to go back a little while to the super techniques where Charles mentioned that it was getting more and more annoying to manage the three different versions of RasterChest. Of course, those being the JavaScript, Java, and C versions. Now, as someone who hangs out a decent amount on various programmer forums, I thought to myself, hey, couldn't we unify two of those, the JavaScript and the Java versions, if we rewrote it in WebAssembly, which is a new, however, byte code type thing that is supported by most modern web browsers. First, the easiest high-level language to write WebAssembly in, or rather, to compile down to WebAssembly, is probably Rust, which is a CI language that includes a horrifyingly large number of compile time and security guarantees. We don't really have to worry too much about it beyond the fact that, well, it's one of the new and important languages, or rather, new and popular languages. So, I looked up a tutorial on how to do this, and yeah, it's a bit of a horrifying mess. However, while I was doing this, I came across a few posts detailing some cool things that you can do with the Rust type system, and I thought I would share those with you. Now, to get into this, I'm not going to give you an entire rundown of the Rust language. By and large, it has a fairly C-like syntax. However, there are a few key points that we're going to need here. Those are generic structs, traits, and rare classes. Now, generics, you already know, they're basically exactly the same as they are in C++. Just use the angle brackets. Things start to get a bit different when we get to structs. You see, Rust has these things called superstruct expressions, which are basically just a shorthand to create a struct with anonymous members. I included just because the example I'm working through uses them very heavily, just for conciseness. So this here is the definition of them from the actual Rust documentation, on with a quick example. As you can see, they're pretty easy to understand. Now, what is a bit harder to understand is a feature of Rust called traits. Now, this is the official definition of a trait from, again, the Rust language specification. Oh, and by the way, if you're wondering why I am just using screenshots from the language specification, just suffice it to say that I am very unhappy with Overleaf right now. Anyway, digression aside, as as you can see, this definition is really not helpful. So let's look at an example. So here what we're doing is we're defining a trait called printable, and it consists of a function prototype. And what we're going to do then is we're going to implement this trait for 32-bit integers. And what we do there is we just provide an implementation for that stringify function. The rest of this is just using that. I like to describe traits as sort of a super version of Java's interfaces, where you're defining a bunch of either function primitives, or in some cases variables, and then you're implementing them, except you're implementing them retroactively after the data type has been defined. There's a whole mechanism for how Rust and its compiler handle these, but we don't really need to get into that. It's a whole ordeal, which I should even entire talk about. And finally, we need something called where clauses. If you've worked with Haskell or some other languages in a similar vein, you can probably guess what this is. It's basically just some syntactic shorter where you can specify properties of a variable before the main body of a definition. Again, this is a definition from the Rust language specification, and I have some examples. Primarily, it involves just cleaning up expressions, so you can say what has certain traits and what doesn't. The really powerful thing, which is in the lower example, is that you can apply it to something more than just raw variables. Cool. So now that we have these building Rust done, let's see how we can use the Rust typing system to perform some very basic proofs. I believe I found this example originally on Hacker News, or maybe it was the Rust subreddit. Link in the description. Either way, we're going to be working through that with some basic arithmetic code. In particular, we're going to be working on some P&L arithmetic proofs. Now, as a quick reminder, right, so like I said, we're going to be doing some basic, very trivial proofs involving P&L arithmetic. So, as a quick reminder, the P&L axioms, these 9 axioms, these are the official versions, and by official I mean taken from Wikipedia. We only really need to concern ourselves with axioms 1, 6, 7, and 8. 2 through 5 are the definition of equality, which kind of follows anyway from first order logic with equality, so we don't really need to worry about them. And either way, Rust will handle them automatically. And 9, which is induction, is really outside of the scope of this example, although it can be represented in Rust also. So anyway, 1 just says that 0 is a natural number. 6 says that every natural number has a So number 7 simply says that the successor function is an injection, and 8 says that there are no negative numbers. So, let's implement axiom number 1 in the rest typing system. We can define 0 very simply. It's just a empty struct. There, that's it. Simple. 0 exists. Okay, moving on. Axiom 6 to 8 are also handled by a single line, which defines successor to be another struct. It's a generic struct taking in the value that we want to succeed, and it contains one field, which is that prior data type. Okay then, that was pretty simple. So how do we use this? Well, using it is very simple. This is how you define other numbers. That's it. Super simple. Now, let's see what we need to do to implement arithmetic. Addition is very simply defined. A plus 0 is A, duh, obvious. And A plus the successor of B equals the successor of A plus B. Again, pretty simple. Multiplication is much the same. A times 0 is 0, and A times 1 plus B is A plus A times B. So addition in Rust comes out to something like this. First off, we need to create an add helper struct, and what this does is it represents the addition of two numbers, A and B. It's again a generic tuple struct. Now we're going to start adding in traits. The add trait simply creates a result type. It's a way of associating the output with the input add helper. So then we're going to implement add in the base case, which is A plus 0. As you can see, implementing can also be generic, and it just involves assigning result to be A. And then we define it for the inductive step, A plus successor B, and with some boilerplate, it just comes down to rearranging terms. So let's say you want to test that. Well, here's how you can show that 1 plus 1 equals 2. We'll create a constant here, which the guy who originally wrote this called QED. He uses an option there simply to wrap everything and make sure it works. If you don't know what an option is in Rust, don't worry, you can kind of ignore it. So what about multiplication? It should just be the exact same thing, right? We define the mult helper struct, which is just there to represent an actual multiplication operation, and a mul trait, which associates the output of the operation with the original mul helper. We just define it for the base case as a 0 case, and then we define it for the inductive case. And by the way, this is where we need where clauses. I did not clarify this before. In addition, in the inductive case, you may see that where clause at the end. What we're doing here is asserting that add helper of A and B already has a matching implementation of add. So here in multiplication, that's what that same whereas is saying. It's asserting that that add helper and that mul helper are already implemented. It's a bit rude and verbose, but it should get the job done. Then we just rearrange the result to be the inductive definition, right? Wrong. Yeah, so it turns out that if you put under rest, that is going to loop infinitely. It's never going to resolve. This is a bit disappointing. Sometimes you have to be a bit creative. Right, so what you have to do to define multiplication in the REST typing system in a way that won't crash is you have to instead first define what the guy who wrote this originally called a helper class. And what it is it's a representation of accumulator plus A times B, which you may remember is the way the recursive definition of multiplication is represented back in the Peano definition of multiplication. From there we have 3 different base and inductive steps. The first one is simply clarifying that a successor of accumulator is the same as the successor of the whole helper. The second is the base case per se, where accumulator is 0 and B is the successor. Actually, I suppose, more accurately, that's an intermediary inductive step. And then finally, you define it for the true base case, which is 0 plus A times 0, which of course is just 0. Now that we have that out of the way, real multiplication just becomes a kind of a typecast, if you will, where mul helper just becomes mul implementation helper of 0 plus A times B. And if you want to test that out, here's the example they included, which just shows that 3 squared plus 4 squared equals 5 squared. Again, these are all super basic things, which you could show by hand, but I think it's pretty cool that you can use the REST typing system to do them. Now, at this point, I want to show you some more in-depth examples of the cool things you can do with the REST typing system. First off, I want to show you that you can actually implement the full Peano arithmetic system with a REST library. You can, it's written, it's out there in REST's Crate Package Manager. Here's a quick look at it. Yeah, so I wanted to cover that in greater detail, but as you can see, it's pretty long. If I wanted to, it would probably be its own series. The other thing I wanted to show you here was that the REST typing system is in fact Turing complete. You may remember I showed you something similar with LaTeX and how it was Turing complete. Turns out you can do the same thing with REST typing system. You can use it to implement an esoteric language, which is Turing complete, called small f. I can't say the full name because this is showing up on YouTube, but either way, it's a really cool example. It's something I found linked to at the bottom of the page that works through the basic examples I showed before. Here's a quick look at it. Yeah, so as you can see, that's pretty long. It's nothing I couldn't cover in a talk, but the issue is, it's dependent on a number of macros that the author has defined, and these macros collectively come out to about 1,200 lines of code. It's probably closer to 500 if you get rid of the comments, but still, you get my point. Way too much for a single talk. So yeah, I am sorry I couldn't talk about that. That's a bit disappointing. So, anyone have any questions about this abbreviated talk? Abbreviated, putting it nicely.